Hello, my name is Alex and I'm going to present this talk in a recorded version so that I will be available for you on Slack, and partially because this is probably somewhere between 3 a.m. and 6 a.m. for my actual time. This work is going to concentrate on 5 or 6 years worth of work by my PhD student Julian Mackay, who has now finished and is working as a postdoc at Imperial College. And he was co-supervised with Lindsay Groves, who's based here at Victoria, and Jonathan Aldrich, who is at CMU and is actually present for this working group meeting in particular. What I'm going to talk about today is polymorphism, or type parameters, or generic types, or many names that you've heard for when you use them to, say, coordinate the items in a list that you're trying to sort. In particular, you often wouldn't just want to denote the parameter of items that are in the list, but describe a little bit more detail about the kind of items that can go into the list. This is where bounded polymorphism comes into play. You may want things that are comparable or ordered or equatable or whatever the word you use, so that you can actually perform a compare to operation or similar to be able to sort the list. These type parameters are also known as Java generics and has been around with us for about 20 years. They have been in many languages, in Haskell type classes, where you can have an ordered elements that go into the list. You also had a more advanced version of them called type members or abstract type members in Scala, where in addition to being able to parameterize methods and objects, you're able to treat them as first-class values so that you can actually look at the object and ask what particular type is involved in a particular parameter of a list. There were various formalizations of type parameters and type members, starting with 30-plus-year-old system FSUP, which also had some issues with things like decidability or being able to check if two types are subtypes of each other and do it in such a way that the algorithm will actually stop. In Scala, the type parameters are a little bit more interesting. They're called path-dependent types. You now parameterize them with a type that is a value alongside things like fields, methods, and type members of objects. You can see a value here, p, that you instantiate to actually have a particular field, a particular method, and a particular type. What that, of course, means is that if you have different instances of that value, so for example, different instances of list, the type will be different depending on the path, hence the path-dependent types. There is good use for this more flexible version of the polymorphism with type members. You can declare a trait in Scala that will have a description for the set of items, and you can identify the fact that these items will be of type element. You can have an insert method that will work with this.lm, which refers to this current instance type of elements. You can then create an object like tables, which will have a table as the type of lm. You can create an object called chairs, which will have a chair as a type of lm. This is assigned in the same way that you will assign to fields, except that it happens to be a type. And then at runtime, if you have chairs, you can insert another chair, such as my couch for the sake of example, and that will work. But if you try to insert, say, a coffee table into the chairs, it will throw an appropriate error. It makes it even more flexible than the parameterized type in Java, but of course makes it even more tricky to reason about these type members and do it in such a way that is decided. But here is where things go wrong, and this will be very similar to the example I used before for Java, only expressed using type members rather than type parameters. So let's say we have a trait called EQ that has equatable types captured, and it will have the type E for the elements, which will be anything. Therefore, I say that at the bottom they're limited by nothing, which is a bottom type in Scala. It has a method compare that will accept elements of type E that will be able to compare these elements, returning a Boolean value, creating a trait set, which is equatable, where the set stores elements like before, type lm, but we also make it extend the trait EQ, and we need to describe what will happen to the type of E that EQ requires to be parameterized with. Well, it will be comparable to other sets. So we insist that at the very least there will be other sets. What will those sets contain? Well, other elements. But what if we want to express the fact that those other elements will want to be comparable? Well, in that case, we will say, well, they're also equatable or comparable. And what are they equatable with? The other elements that also have a type member E. That also will need to be, in turn, to be compatible with the element type LM. The thing that happens here is that you basically say, this is the best way that I have to express the fact that I have sets that are comparable to other sets that in turn contain elements that are comparable among each other. That's fine. What can possibly go wrong? Except, of course, the setup is a little bit convoluted on purpose. If I were to then instantiate such set by having, say, a class tree that's going to have elements inside that are of type tree that also happens to extend such set, and then if I were to ask myself, well, is this tree going to be containing elements that are equatable and have the type E, that is, at the very least, other tree objects that we are comparing them to, the type checking algorithm is going to end up having to do the following. It's going to expand the tree by the declaration to be a subtype of set of things that have the type LM with them, that is a subtype of tree, still comparable to equatable. It will then go and look at the declaration of set that I've written earlier and say, well, that's going to have to be a subset of EQ that has the type E, and this is where I have to write out the fact that it's other sets that have the element type LM that is also equatable in turn. And this is actually what causes some of these loops. What happens here is contravariance. So to compare the two to be subtypes of each other using the contravariance, where the bound is actually needs to be a supertype of tree and set respectively, it's equivalent to then comparing the tree being a subtype of the set, swapping them around. And of course, what that results in is that if you look at the declaration of set and tree, the tree has to be expanded to set, which has the type element, subtype of tree, and when you expand that, you end up back to where you started with tree having to be compared to an equatable. So I, in some ways, tricked the type checker, but I didn't do anything particularly wrong by basically utilizing the power of being able to use bounded polymorphism to get it to loop forever. Now, while it is rare and as a result not many language implementers deal with it, for us as toolmakers and static analysis people, we actually want to help both the tools that we write and help guide the programmers when you do see the error like that with slightly better error messages than going into a Stack Overflow or a loop problem. So what Julian did over the past 6 years and a lot more than 6 years is provided at least 3 decidable variants of particularly concentrating of Scala, working with dot calculus, where the insight was that one thing you can do is you can fix the types to a particular context they're defined in, and thus avoid the problem that happens as you set up the types in a loop, potentially expanding forever, by rather associating each type with a particular context and being able to tell that you're dealing with different types rather than going back to the same question you started with, such as trees at a subtype of EQ, thinking that it is still the same tree. It's a similar idea to DSAP work that Andre, who is also potentially here, but is a member of this group anyway, has proposed at the same conference as us in Popl 2020 last year. Julian then also proposed another version, which is similar to one of the proposals for the system F sub, where you can simply prohibit recursive subtyping and not allow people to declare types that mention themselves in their declaration. And this is the version of solution that Scala compiler basically does, because it is easier than doing a lot of restrictions, but then there is quite a lot of interesting structures that you're no longer able to express as a result. So we'll call it a DOTI solution. But more interestingly, we explored extending what was Ross Tate's solution about placing syntactic restriction on when you can use recursive types safely and when you cannot use them. And we call them materials and shapes in the same way as Rostate did. And we've implemented a solution that with that allows you to have a decidable subtyping algorithm that is still expressive. And in fact, we had a slightly later paper in Atlas 2020 in December last year, where we've showed how to extend the solution in general to bounded polymorphism and allow you to have still usable, and we argue in most cases the code that you write will be within the restrictions that we impose, although we need a larger corpus study to confirm that, decidable subtyping variant, which we've demonstrated that can extend both system F sub setup and also D sub setup for the Andre's version. So the second paper that I mentioned generalized this approach. This was in December last year, that showed that you can just achieve simple syntactic restrictions and achieve decidable subtyping. That's all you need. The basic idea is that for any kind of system that you take that has the type members and problem with the decidable subtyping, you always are able to define a syntactic subset that is decidable and yet expressive enough. So we've done it for system F sub, we'll call it system F sub restricted. And as opposed to very strict changes, like let's completely remove contravariance or completely remove recursion and things like that, ours allows one to still have all of this transitivity, all of the normal performance of the types that you would expect, and yet allow you to write the programs in such a way that we think follow what programmers expect, using what we call restrictive types in case there is a possibility of recursion. So the bounds here are using a restricted type. So you get decidability, you get the type safety and all of the nice properties. You get subtype transitivity and ability to tell the programmer when something goes wrong, and yet we hope that our restricted version covers all of the common programming paradigms. And while we still haven't done the actual study, that's an obvious next step of the Scala code, we think the normal code that people write with type members will be within our restrictions. So there you go. There is the 3 decidable variants for type member usage that we've designed, and a generalized syntactic restriction idea expressed later on as a result of that work. And a lot of connections and help, hopefully, to the tools that want to handle type bounded polymorphism within type membership, shape or otherwise, and be able to rely on things as simple as subtyping checks actually terminating rather than carrying on in a still acceptably usable expressive code. Thank you very much.